So take the gamma hat, divide by sigma hat. This now gives you the t test for gamma hat, right? But the key is not to compare it to the t table, because we know that this cannot be compared to the t table. Okay? We know this cannot be compared to the t distribution. So what distribution do we compare it? Okay, and the point is there doesn't exist a well specified distribution which you can compare it to. There doesn't exist a table. Like an F, T, chi-square, these are all distributions for which tables exist, right? There is no such distribution which gamma hat follows. There is no particular distribution that they follow, right? So how do you compare it to a distribution? How do you take a test of that? You do as follows. That is why, that's what modern computing technology comes in handy. What they will do is, suppose I have got 50 observations. And suppose I want to test whether gamma is equal to 0. Right? I will test gamma is equal to 0 or phi is equal to 1. Right? Gamma is equal to 0 or phi is equal to 1. Then what the computer will do is, suppose I got 70 observations in my data, then it will generate a random walk of size 70 on its own. Right? So it will generate one random walk of size 70 on its own. Do this test. Right? Calculate the value of t gamma hat for that one sample. Then it will generate another random sample of size 70. Again get a t gamma hat. Again regress yt, regress delta yt or yt minus 1. Get another t gamma hat. Do this thousands of times. So it will get the distribution of t gamma hat under the null hypothesis. Then it will plot the distribution like this. Okay? Plot it. This will generally negatively skewed here. And it will say, if my calculated value is less than the lower 5% quantile, I will reject the null hypothesis or I will fail to reject the null hypothesis. So in every case, the simulation has to be, the t distribution has to be simulated. The distribution here has to be simulated. And this distribution is called the Dickey-Fuller distribution. Right? This distribution is called what Dickey-Fuller did really, both Wayne and especially Dickey, in the paper in Econometrica in 1982 is, because those were the days when there were no fast computers. Right? So what he did was, he actually for different sample sizes, he actually tabulated these values by running these simulations. You must have had to do it thousands of times manually on a facet calculator or those big, those days were very different in 1982 and 83, etc. Computers were very different from what they have today. Right? In 1989-90, I think I had a computer which my friend said was way beyond what my needs was. When I had spent splurged a lot of money getting such a powerful computer. It had a hard disk of 20 MB. Right? And it had a RAM of 640 KB. Right? That used to be the RAM of a computer, 640 KB. Right? And it took you about half an hour or 45 minutes to run a single regression. If you have a large regression, it takes a lot of time. Right? So those days where it was intercomputation was very expensive. And that is when Dickey actually calculated those tables. So if you have a sample size of 25, what is the distribution for that t test? Right? The distribution of this. If you have sample size of 50, what is the distribution? Sample size of 100, what is the distribution? What he also did was, now clearly, how are we generating these tables? We are generating these tables by running a regression. We are regressing delta yt on gamma yt minus 1, right? On yt minus 1. First we generate a random walk, then we calculate delta yt. We ask the computer to generate a random walk, which we will call yt. Then we take each value of yt minus the previous value of yt as a dependent variable, previous value of yt as the independent variable, do this regression, calculate gamma hat by sigma hat gamma hat, do this thousands of times, you get thousands of t gamma hats, and you plot the distribution and see what is the lower 5% cutoff or lower 2.5% cutoff or lower 10% cutoff and so on. So very computational intelligence. Now the problem here is, of course, if there is an intercept in the regression, then the underlying distribution will change, because you have to do a different simulation, right? So what Dickey also did was he calculated these tables for various kinds of forms. Now fortunately, your desktop computers do it in a jiffy. Okay, but the tables are still known as Dickey-Fuller tables. Right? So what you have to do is what is called a Dickey-Fuller test. Okay, what you do is what is called the Dickey-Fuller test if you have non-stationary data. Right? You have got non-stationary data. And we'll learn more about the Dickey-Fuller test in the future. It was immediately realized that instead of doing this, instead of running this regression, if you actually ran this following regression, see, so if you included some values of the dependent variable, some lag values, some previous of the dependent variable as independent variables, you get better results. The power of your test increases. This is called the augmented Dickey-Fuller, because the delta yt has been augmented by delta yt minus 1 and the regression is there are more experimental variables here. This is called the augmented, and the test is called the ADF test, augmented Dickey-Fuller. Whereas if you just do this is called the Dickey-Fuller test. Called the Dickey-Fuller test, where this is called the augmented Dickey-Fuller test. Okay? So in the next class we'll learn more about, and in really being able to carry out Dickey-Fuller test for different kinds of more complicated specifications, you will learn if you take a paper called Time Series Econometrics in your third semester, which essentially tells you about mechanics of time series. And if you take another paper in your fourth semester, hopefully it should be offered on time series 1, which will tell you all about the mathematics of time series. Right? Which is a different ballgame altogether. Because if you don't have t-test, f-test, z-test, then how do you deal with the maths? How do you take tests of hypothesis? Right? How do you deal with non-stationary data? The formal, how do you prove, for example, things like the central limit theorem and all those kinds of things? Right? Okay? So that's, because you know the idea of the central limit theorem, right? If yt is a normally random variable, okay, so yt is a variable with some known mean mu and some constant variance, then the mean of yt, right, will be standard normal distributed. But if yt doesn't have a well-defined mean and well-defined variance, the whole thing becomes a problem. So you need to deal with it more formally, right? More formally, the mathematics becomes more complex. If you take a time series 1 paper, you will actually be able to deal with that. At least learn how to deal with that. Sure? So thank you very much for coming on a Saturday afternoon. Right? My apologies, but we had to miss some classes and we need to learn these things. I can't let you walk around with an econometrics program without learning something about time series. So we do. Sure? So thank you folks.